This morning's lectures from me will focus on optically thick gas in the universe. Most of the discussion, although the formalism I introduced for this frequency distribution of the column densities is generic to any column density. Most of the discussion yesterday was focused on the lower end of this frequency distribution, the putative intergalactic medium, which I'll come back to tomorrow. But for today, I'm going to focus on the higher end of the distribution function, the optically thick gas, which we'll see is column densities above a few times 10 to the 17. And the second lecture this morning will focus on the damp Lyman-alpha systems, which is the very high end of this frequency distribution. I guess, yeah, I've got two boxes here, and it's not coming out quite so well, but strictly speaking, a Lyman limit system is any blob of gas that is optically thick at the Lyman limit. So that implies a lower limit to the H1 column density, which means any system boxed in here and all the way out to infinity is included within that definition, although scientifically one often distinguishes between the damp Lyman-alpha systems and the gas in between, which are, say, from around 10 to the 17 to 10 to the 20. It's a bit of a technical detail, but a fact in the literature. So I will introduce to you the astrophysics of the H1 continuum opacity. I'm not going to go through the full quantum mechanical derivation, but show you the bits and pieces that lead to it, and at least explore the cross-section, which is plotted here for that continuum opacity. It's obviously not a line opacity, it's a continuum opacity, so that it's sensitive to essentially all energies above the ionization threshold, although the cross-section does peak close to the energy threshold of 1 Rydberg for hydrogen. We'll define what a Lyman limit system is, and we can explore a little bit of the data, but it's again, a significant amount of hydrogen gas sufficiently dense, sufficiently optically thick, such that you attenuate of order optical depth of unity or more at the Lyman limit, at the continuum of hydrogen. We'll describe how the incidence of this gas is measured throughout the universe. It's pretty analogous to the discussion we had yesterday for Lyman-alpha forest lines. And I will derive empirically for you and show you the techniques used to estimate the mean free path, which is a cosmological quantity, how ionizing radiation is attenuated by our universe here as a function of redshift. And I'll say a few words linking this gas to this optically thick gas to gas around galaxies as predicted in numerical simulations, one of which is shown here. And though this is a conference on hydrogen, I may give you some context of the metal enrichment of this gas because I think it's kind of, it's quite exciting. All right, so those are some introductory slides. Let me dig in back into the notes. I think I've covered most of the motivations here. The optically thick gas, cosmologically speaking, is what attenuates our radiation field. So you have an interplay between the ionizing sources of quasars and galaxies and the optically thick gas in the universe, and together we can calculate the mean intensity, the extragalactic UV background, EUVB, in the universe. We also theoretically, as I just showed you in cartoon form or in simulation form, expect there to be physically a link between this optically thick gas and the interface between galaxies and the intergalactic medium. That's at least what's predicted from simulations. We expect the dense neutral gas to be within the galaxies. We predict and find that diffuse, highly ionized gas is far away from the galaxy's intergalactic medium. The optically thick gas kind of lies somewhere in between, a bit of a Goldilocks, if you will. Okay, so continuum opacity, this is bound free absorption. We start with a bound hydrogen atom and wind up with a free electron. You have a photon of energy h bar omega, which exceeds the ionization potential, strikes the hydrogen atom, and then you have an ejected electron. Conserving energy must have h bar omega minus IH. And it's a continuum opacity because that electron can carry away continua of energies. Classically, you might think there's an infinite number of energy states that electron can take, but of course that's not true quantum mechanically. Our goal to estimate that cross-section is to combine an expression for the probability of the absorption with the density of the final states for that free electron, which I'll cartoon for you in a moment. and use that to estimate the overall cross-section. So just a simple illustration of the process here. Incident photon onto a hydrogen atom, giving you a free electron and a free proton at that point. All right. We can describe the wave function of this free electron as being normalized within some very large volume, L cubed, so that the wave function looks something like this. Okay. It's got a final momentum, kf, so a final energy, p squared over 2m, which is just h bar squared kf squared over 2m. And in quantum mechanics, the typical approach to describing the quantized states of a free particle, like this electron, is to demand that the momenta take on quantized values, integers, nx, 2 pi nx over L, for each of the 3 momenta vectors of the particle, so kx, ky, and kz. And then what we're really after here is the density of states. So visualizing these 3 momenta, nx, ny, and nz, analogous to, or just directly the case for spherical coordinates, the density of states for this 3-dimensional system is simply n squared dn d omega. And we relate that then to our density of states and energy, which is what we're after, G of E being the density of states. Okay, so again, the probability is dependent on the energy states that the free electron can wind up with, and we need to take into account the degeneracy of each of those energy states, and we can relate this G of E back to the quantized momenta of the free electron. So that's what these notes here say. I won't repeat them. Here's the expression for G of E then, L over 2 pi squared me over h bar squared kf. That gives us our density of states. And now we recall, and Mark emphasized this in his lecture, that the cross-section is the energy absorbed per unit time by the atom over the energy that was incident on the atom, so the h bar omega, or the intensity of that energy that was incident on the atom. Without derivation, this is the transition probability per unit time for our bound-free transition. Don't worry about that so much. But the differential cross-section then is the probability of the transition, the density of states of our final electron, the incident energy, the energy absorbed, which is h bar omega, and the instant intensity. So I don't even have in the notes the full quantum mechanics. That's plugging and chugging to get the cross-section per unit solid angle. And I'm just going to jump to the final solution under the dipole approximation, which is this. It's actually best to see that. A bit messy. We wind up with what appears to be a nu to the, or a frequency to the -4 dependence in the photoionization cross-section, but there's this f of eta term, which is quite a complex function of the frequency, so that it's not quite, in fact, it's not nu to the -4. You'll see in a moment that it's more like nu to the -3, close to the ionization threshold, and decreasing from there as you go far to higher and higher energy. So let's look at that now. Here's our photonization cross-section. There's the f of eta that pops out of the quantum mechanical calculation with a dipole approximation. Here's the photonization cross-section, peaking around 6 times 10 to the -18. I'll come back to that number in a moment at 1 Rydberg, and then rapidly declining with increasing energy. And the frequency dependence is complex. If you assume some power law, that sigma goes like nu to the -alpha, then d log sigma, d log nu is just minus alpha, and that's what's plotted here. So the power law exponent, let's see if I can put that. the power law, the exponent of that power law expression for photonizing cross-section. It's quite close to -3 at the ionization threshold. It's actually more like -2.7, and it goes to -3 as you go to a fewer Brigg and becomes steeper as you go farther out. Okay. For somewhat of completeness, many folks take advantage of the Werner et al. Approximation for the photonization cross-section, so you might want to check how valid that is. So I did, because I myself tend to take advantage of it. Oh, got to calculate it first. And you can see their approximation was just some polynomial approximation to the hydrogen atom. And actually, they include calculations for many other ions. It's an excellent approximation over orders of magnitude and quite a few Rydberg. If I try and zoom in, eventually you'll see some difference between the two, but it's an excellent approximation to that pretty ugly looking f of eta term and so forth. There we go, finally some difference. Okay. So that gives us our cross-section to ionizing photons. As I mentioned from the plot, the ionization right at the energy threshold is 6.34 times 10 to the minus 18 square centimeters. And so we can ask rather simply, what's the hydrogen column density now? And coming back to our hydrogen gas, what's the hydrogen column density required to give you an optical depth of unity? And it's obvious. We just take 1 over sigma, and that works out to 10 times 17.2 particles per square centimeter. So that defines what is optically thick gas for a tau of 1, which is a sensible choice for what we will call a Lyman limit system. Any questions on that? Continuum opacity, and a definition, if you will, or a calculation of the amount of gas necessary to make you optically thick. So a Lyman limit system, in the terminology of the intergalactic medium or the Lyman-alpha force, is an absorption system that's optically thick at the Lyman limit. It's not necessary that we take tau equals 1, but let's just do that going forward. Sometimes when you actually work on the data, you might adopt a slightly higher optical depth value just to be able to survey the systems. It's a bit of a detail. At this column density, the first 10 lines roughly of the Lyman series are highly saturated, and you'll see in the data itself that the blend of the higher order Lyman series, not surprisingly, that the optical depth of the optical depth of the blend of the higher order Lyman series moves on smoothly to the continuum opacity that we just derived for the continuum. So let me show you a quasar. This is from the VLT X-shooter survey. That's just a plot. We can skip over that. Let's do this. Data. Fine. So here at around 4,900 angstroms, we see a strong break in the continuum of this quasar. It's due to the continuum opacity, not due to line opacity. And you can appreciate that because the flux remains low over many hundreds of angstroms blueward of the Lyman limit here. And I just wanted to show the distinction or the behavior of the Lyman series for such gas. Hydrogen. It shows roughly the first 20 Lyman series lines. And that's 937. No, it's not. That's 949. Yes, it is. Okay. Just tune it up a little more. So you can see the Lyman series opacity, or the Lyman series lines, higher Lyman series lines. As I said, they're highly saturated, even for tau of 1, up to maybe the first 10 lines. And then as we approach the Lyman limit, they blend together, and you get a optical depth from just the Lyman series lines, which matches the continuum opacity that you see blueward of the Lyman limit. And out here, I don't know, just for completeness, must be Lyman-alpha. There's Lyman beta, and fine, a Lyman-alpha line associated with that optically thick gas. So this material has about that tau of 1, or a total H1 column density of 10 to the 17.2 or so. Not something that could be derived from the Lyman series lines themselves, but the continuum opacity is directly proportional to the column density, and you actually can very precisely measure the total column density here from that decrement, from the flux decrement, red root of the Lyman limit to the blue root of the Lyman limit. That ratio gives you a very precise measurement of the H1 column density. Good. So that's an example of real data. Of course, in flux space, which is where we observe, we only have sensitivity to opacities or optical depths ranging from about 0.2 to 2, so maybe 1 order of magnitude in the optical depth, from going from no absorption detectable to so highly absorbed you can't tell if it's tau of 2, tau of 10, tau of 100, which means you only have about a factor of 10 sensitivity to the column densities. As a result, when I talk Lyman limit systems, or when anyone talks Lyman limit systems, as I said at the start of this presentation, you're really describing any gas that's optically thick, and the column density is from 17.2 to infinity. You're really generally not sensitive to the total amount of gas, other than there must be enough there to absorb most of those photons. Any questions on that? Okay, let me say some words now on how we estimate or measure the incidence of such optically thick gas in the universe. It's a little bit different, or it is different, than really any other survey for gas. Again, we'll use quasars as our light sources. Light traveling towards us. Here's another quasar. It's a survey. Another quasar. Let's do one more. Okay. And there will be optically thick gas along several of these sight lines. There you go, blob optically thick gas. Unlike our survey for Lyman-alpha lines, or our measurements of the Lyman-alpha force, and unlike if you were studying damp Lyman-alpha systems or any other type of absorption in the universe, magnesium, carbon, whatever it is, with the Lyman limit systems, as you've just seen, they remove the flux of the quasar blueward of their appearance. Okay, so in this survey, let's put a Lyman system there, let's put a Lyman system here. Maybe I'll not have any there, and one here. The search truncates at the presence of the first incidence of optically thick gas, and so you wind up with detection, and no sensitivity to additional detections blueward of that lower redshift than the first one that you've observed. Okay. We use quasars again because they do emit radiation blueward of the Lyman limit. That's actually rather surprising when you think about it. Here is the spectrum of a single quasar showing radiation all the way down to 700 angstroms in the rest frame. Remember, this accreting black hole is within a galaxy, we believe, and have demonstrated, and usually even star-forming galaxies at high redshift with lots of gas around, yet somehow, or not quite clearly, they have managed to photoionize all the gas within that galaxy such that they are emitting freely down at energies of 1 Rydberg and beyond, which is, say, the escape fraction in most quasars is of order unity. Okay, that allows us then to do the experiment I've just cartooned. When you actually work through a calculation in photoevaporation, indeed type 1 quasars are bright enough to photoionize the gas out to a megaparsec around them. Okay, so David Tytler had the insight to first describe the surveys, an estimate of, or the analysis of a survey like the one I've cartooned on the board in terms of survival statistics. You might appreciate are what people use to calculate the incidence of failure of car parts or the incidence of failure of human beings. But it's the same kind of concept here. It's the incidence of failure of flux, really. How far one goes before a failure of a part, or in this case, before hitting a Lyman limit system. you could describe the survey with three distribution functions or three density functions. He's defining T, kind of using his formalism. He's defining T as the distance traveled from the source, which is at some redshift, say Z emission, to the absorber, which is at the redshift of the Lyman limit system or the hydrogen gas. And so T is just this distance. Okay. Here, when I've got no absorption, no absorber, the T is the full path of the quasar until we hit the end of the spectrum. And you have three descriptions of the data. You can have the observed distribution of redshifts of the systems. So just looking at the way I've cartooned it, if you just naively took the redshifts as observed, you would say, well, the universe must have a lot of optically thick gas here close to the redshifts of the quasars and no optically thick gas in the universe down here far away from the quasars. But of course, that's not the case. That's just because we're not able to observe the gas down here far away from the quasars because there is optically thick gas up here close to the quasars. So F is just the observed distribution of the redshifts of the optically thick gas. S, the survival function, is the probability that no Lyman limit system occurs in some interval. All right. And that's just 1 minus the integral of this F. And lambda, as he defines it, I will use L as before, is the distribution function we're interested in. What is the true distribution of optically thick gas in the universe, not the observed distribution from our experiment. And so you get to apply, or he did apply, survival statistical analysis to calculate this L. I'm not going to go through it, see his paper. It's rather nice, actually. But 30 years ago now, he made the first estimate for the incidence line density of optically thick gas throughout the universe. This was his first estimation. The modern approach is not to use survival analysis, although it's based on it in some level. We will define a sensitivity function, G of Z. And that is the G of Z will describe the number of sight lines where one can do the analysis. And again, this is like the survival analysis, where one can make the measurement for a Lyman limit system. So coming back to my experiment here, the G of Z function will be the sum of all the path length where I can see a Lyman limit system. So for each of these quasars, this has the smallest G of Z. Okay, we were only able to detect Lyman limit systems between the start of the quasar and out to where we actually detected optically thick gas. For this quasar, we could have detected it all through it. Here, just a smaller path, and here, this even smaller path. So G of Z is, for each quasar, is the search path allowed for the optically thick gas, which goes from the quasar itself to the end of the spectrum or the first incidence of an optically thick absorber, whichever comes first. Here is an example from one of my own surveys. So G of Z is just the number of quasars, or how many, as a function of redshift, how many quasars we were able to observe, able to search for Lyman limit systems. And even with the full Sloan survey, that only numbered in the few hundred out here at a redshift of 3.7 and above. Okay, so then the incidence given that G of Z function, which is our search path, similar to what we described for Lyman before, the incidence of Lyman limit systems is simply the number of systems detected in some redshift interval over the sum of that redshift survey path detected. Makes sense. Number of systems over the amount of path we surveyed. Again, you can estimate the variance from the Poisson statistics. Here's an example of a bin evaluation from that same Sloan survey. And similar to what David found 3 years ago, but now with considerably better statistics, we see an incidence that rises with increasing redshift. Again, similar to the Lyman force, but now in the optically thick gas, we also observe an increasing incidence of highly optically thick material as we go to higher and higher redshift. Also, similar to what we did for Lyman forest, you can adopt a maximum likelihood analysis to measure that incidence. I'll just remind you, the concept is very much the same as what I described yesterday. We divide our volume into a number of cells. Now the cells are in redshift space because I'm solving a model for the variation in the incidence with redshift as opposed to column density space. And the mu, as we defined it yesterday, now is equal to the incidence per unit redshift times the size of the cell in redshift space, delta z. And we perform the same swindle, let that delta z go towards 0, and the Poisson probability is either that for 0 or that for 1 in each of these little cells. As yesterday, we're motivated to look for a model of 1 plus z to the gamma. And that's true, I didn't yesterday go through this. As I said yesterday, the likelihood technique then gives you the best parameters for that model, so the gamma that we're after, the power law exponent for the redshift evolution. It doesn't tell you whether you have a good, it doesn't on its own tell you whether that model is statistically sensible. The general technique then is to do a KS test comparison between the observed distribution of redshift distribution of the Lyman limit systems, which I'm plotting here for somebody else's survey. Black is the data. So every time there's a Lyman limit system, you just get a step up in the cumulative distribution function here, and red is the model, the best fit model to the redshift evolution given the survey path. And you can perform a KS test on the two cumulative functions to assess whether that model is a good description of the data. And indeed, you can tell by eyeball even that it is. So spanning over most of the universe, the red line is the best fit model for the redshift evolution of optically thick material from 0 to 5. Again, increasing even quite rapidly at the high redshift end. And there's the parameterization and the numbers in the notes. From that incidence, you can directly calculate at a given redshift, say 3.5, what the separation is between optically thick absorbers. Where physical distance here. So again, I introduced this yesterday. dRdz is just c over h, z times 1 plus z. And we derive that this mean separation at redshift 3.5 is about 100 megaparsecs, which exceeds the separation between at least faint quasars by factors of a few, maybe even a factor of 10. Which is to say that any material at a redshift of 3.5 can see multiple ionizing sources. While the incidence of these optically thick gas is high, the separation is of order 100 megaparsecs. And on that scale, in a volume or in a separation of 100 megaparsecs, you're likely to have several ionizing sources and see several ionizing sources at one time. So you're not just dominated by the closest local ionizing source to you. One implication. It's just delta R plotted versus Z. So 100 megaparsecs at a redshift 3.5 and rising rapidly with decreasing redshift. There are some subtleties to this analysis. I'll just emphasize one, which is that the Lyman limit systems themselves attenuate the colors of the quasars. So I don't know, this example here where the light was absorbed really close to the quasar, if that quasar is, say, at a redshift of 3.5, then its U-band flux, its ultraviolet flux, has been greatly attenuated by the continuum opacity. And so if you have a survey that selects quasars by color, like the Sloan Digital Sky Survey or the BOSS survey, then the intergalactic medium is actually biasing, or can be biasing, the quasars that you discover from such a survey. And that really hits home in a somewhat subtle manner. It's a complicated plot. Let me walk you through it. It's color space, U minus G colors, so down there in the blue, G minus R colors here on the y-axis. The blue, hopefully you can see it in the back, contours here are point sources, stars, in the Sloan Digital Sky Survey imaging. The red are extended sources, galaxies. Okay. So that's the color space, the stellar locus, if you will, of our Milky Way in this color space. The cyan curve is the colors that one predicts for a typical quasar SED as you go from 0, the redshift 0 quasar, out to a redshift, I think, 6 or 7 in this analysis. Okay? And you depart from this color, which is what you're measuring here is the so-called UV axis. You depart from this color at around a redshift of 2.6 or 7. So quasars at redshift 2.7 have colors that are very similar to the stellar locus. And I'll remind you that quasars are essentially point sources, so it becomes nearly impossible from optical imaging alone to distinguish between a quasar and a star, a quasar at 2.7 and a star in the Milky Way. As a result, the Sloan survey didn't target sources with colors like this because they did not want to detect a whole bunch of galactic stars. They were at least not in the first go-around. And there's where the bias comes in, but if you have a Lyman limit system, that will actually redden this U minus G color and push you outside of the stellar locus into color space where it can't be a star, shouldn't be a star, instead is a quasar. As a result, when it came to quasars around a redshift of 3, the Sloan survey picked out systematically quasars that had Lyman limit systems in front of them, optically thick gas that absorbed the U band flux and pushed them out of the stellar locus. And we tripped upon that ourselves when we were doing the survey. For the incidence, the green points here are the incidence you would measure if you used all the Sloan quasars and measured the incidence down of H1 gas, optically thick H1 gas down to 3.4. But this apparent rise in the incidence is not due to the fact that the universe has more optically thick gas at that redshift. It's due to the fact that the quasars that made it into the Sloan survey have more Lyman limit systems in front of them than the actual universe does. So we wound up having to throw those quasars out altogether and carry on with the analysis. Skip over that.
So that's why you have all the gaps at 2 to 3 in the previous 2 plots?
No, the gaps at 2 to 3 is observational. The 3 has actually been filled in recently, but to do the analysis of a optically thick gas at redshift 3, that puts the Lyman limit at 4 times 900, which is 3,600 angstroms. That's bluer than the Sloan survey. We had to carry out our own dedicated survey down to the atmospheric cutoff of 3,200 and able to fill in that redshift range. Yeah. And then these data, of course, require the Hubble Space Telescope because now you're talking about true ultraviolet wavelengths. Mm-hmm. Good question. Okay. I've danced around the absorption path previously. Let me now explicitly describe it and define it. It was originally, this is x of z or dx. It was originally introduced by Bacall and Peebles to use absorption line data as a test of cosmology. So they introduced x or dx so that the incidence of absorbers per unit co-moving density times physical cross-section would be constant as you traveled in time, as you traveled through redshift space. Okay, so it's defined so that the product of NC, the co-moving number density of your absorbers, times AP, the physical size of your absorbers, would be would be the quantity that you're measuring. And if those are invariant with redshift, then so too would be this incidence that you measure as the product of the two. So, as I said, I kind of danced around this when I was talking about the Lyman-alpha force. Let's now just do this explicitly. We start from the same starting point as I used yesterday. The incidence per physical path that you travel through a box of absorbers or of gas, it goes like the number density of those absorbers, physical number density of those absorbers times the physical area of those absorbers. I won't draw the cartoon again. But just think of a box with systems within it. We know how to convert dr physical to dz. That's all I've done there. And then now I we want to introduce this x quantity, absorption path, dx, such that we have a quantity that goes just like the product of the co-moving number density times the physical density times some constant or some number. And if you want a dimensionless quantity, then it's convenient to use equation 33. So this is the definition of this dx quantity, h over the Hubble parameter times 1 plus z squared. It takes out of the 1 plus z factors that come in from the co-moving number density and the 1 plus z that comes in from the physical size as a function of the physical size from dr dz. And altogether you get this, which is pretty simple. So we've measured previously the incidence per unit redshift. Now this is the incidence per unit x, this absorption quantity. And it's defined, as I said, so that L of x is proportional to just the product of the co-moving number density and the physical size of the absorbers. And again, the Bacall and Peebles were initially motivated to introduce this formalism so that one could survey the incidence of gas, say optically thick gas in this case, across cosmic time. And if they had the right cosmology, and if that population was non-evolving, let's say it the other way, if that population was not evolving, then they could solve for the correct cosmology that would give a constant L of x as a function of redshift. Today we have a pretty good understanding of our cosmology, and we can invert the problem and look for evolution in this product of the co-moving number density and physical size. This is just dx dz. I'm just showing you explicitly what dx dz is as a function of redshift. So I've shown you the estimation of L of z, and it's just the Jacobian transformation to get to L of x multiplied by dz over dx. So doing that, here's what L of x, the incidence per unit absorption path, looks like as a function of redshift. It's not constant, clearly, which is to say that product of the co-moving number density of optically thick gas times the physical size of this optically thick gas must be evolving. It must be decreasing, obviously, from the plot, and decreasing quite rapidly by a factor of about 4 or so, from redshift of 4 to 1, which is a bit of a surprise. You can model this, say with a toy model, under the assumption that optically thick gas is associated with dark matter halos, and I said I'll make some more arguments that it at least should be some of that gas, a significant amount of that gas should be. Then we can make a simple toy model for this L of x quantity. Integrating over the mass function of dark matter halos, which we have from cosmology. This is the co-moving number density, at least per log virial mass. This is the physical size, pi r squared, say for the virial radius, out to the virial radius of a dark matter halo, and some fudge factor, if you want to call it that, for the covering fraction, how much of that virial halo actually has optically thick gas covering it. That's an unknown and something we just model here, and the C over H naught that comes in from dn dx, L of x. So taking the initial ansatz that this quantity, the covering fraction times the size of the virial radius, is a constant, if we assume that there's a constant covered amount of optically thick gas in halos, then the fact that we have hierarchical cosmology and the buildup of dark matter halos across time leads you to predict that the incidence should be strongly increasing. So the red line here is the curve for that ansatz. We're assuming that every halo has a constant covering fraction of optically thick gas, and that the only thing that's changing is the number density of halos. And of course, the number density of halos in our hierarchical cosmology increases rapidly with redshift, or decreasing redshift. And that's obviously not a good description of the data. So this decline that we observe in the optically thick gas runs really contrary to the expectation of a hierarchical cosmology. And we then evoked some other very simple scenarios, say for gas being expelled from dark matter halos, some kind of wind scenarios, some accretion scenarios of those blue and green lines. They do an okay job, perhaps, of explaining the evolution, the small evolution down here, low redshift, but still can't describe, it's very difficult to describe this very rapid increase in optically thick gas as we head back to the epoch of reionization. And we're somewhat forced to ascribe this material with gas outside of dark matter halos. I wouldn't say we've exhausted all possibilities for placing gas within dark matter halos, but certainly simple models won't work. All right. I have about 5 minutes? Yeah, okay. Any questions first on some of the implications of optically thick gas? Fine, so I'll introduce the concept of the mean free path, and then we'll pick up in about 2 hours, I think, with actually calculating it from the data, or estimating it from the data. So definition, mean free path, well, at the top level, this is the attenuation of ionizing photons through the intergalactic medium. I will specifically define the mean free path as the physical distance that a packet of photons travels before it suffers an e⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ This, of course, will depend on the source redshift, whether your source is at redshift 4, redshift 3. Then the amount of opacity that those photons suffer will be different. Let's define also an effect akin to the effective opacity of Lyman-alpha. Let's define an effective opacity from the Lyman continuum. And we will then couple tau effective of 1 with this mean free path. That gives you this e to the minus 1. The somewhat subtle concept is that the longer and longer mean free paths we measure, that's actually corresponding to higher and higher energy photons emitted by the source. And I'll just walk through these slides before quitting for now. Come on. Not that, not that. Fine. There it is. Okay. So quasars emit ionizing photons as well as lower energy photons as well. And a way you may, I've kind of color-coded the photons of the quasar, emitted by the quasar in its rest frame, to those that are ionizing photons in blue and non-ionizing photons in red. The red ones, of course, give rise to Lyman-alpha force, and the blue ones are what allow us to probe to the optically thick sources in the universe. When I visualize the spectrum, I see distance, not just energy and wavelength. And here's what I mean. Consider a quasar. I'm going to put it at a redshift of 4. If I now view the red photons, those that are non-ionizing, those just travel to Earth. There's no, they never were ionizing photons blue. They were always red. If I consider a photon that has an energy of 1 Rydberg in the rest frame of the quasar, it travels a very infinitesimal distance before redshifting and becoming no longer an ionizing photon. If I consider a 1.02 Rydberg photon that's 900 angstroms, it'll travel down to a redshift of 3.92, or about 10 megaparsecs, before redshifting beyond 1 Rydberg and no longer being able to see the continuum opacity, or no longer being able to ionize the gas. And then, 1.2 photon will travel 100 megaparsecs. So the higher energy photons then will probe more and more of the universe for this ionizing material. That's kind of the subtlety of the concept I mentioned. The arrows here just show the 4 photons. Now put in some gas. A hydrogen gas that will absorb ionizing photons according to this mean free path. The photons that have lower energy, of course, pass through that gas. They can't be absorbed. They don't have sufficient energy to ionize the hydrogen. Now consider this 1.02 Rydberg photons here. I've had it travel the full 10 megaparsecs without ever being absorbed. It then has energies below a Rydberg and continues on through the universe. Now here's a case where this photon would have traveled to 100 megaparsecs, but instead was absorbed by the hydrogen gas out at around 30 megaparsecs. Okay, so in order to probe this mean free path, we have to use the full range of energy of photons emitted by the quasar. This is what we've seen actually in this one example, is that the ionizing photons here were absorbed at a 30 megaparsecs in front of the quasar. Okay, but that's just one quasar. When I pick up the lecture later, we'll describe how we go from one observation to a measurement of the average mean free path in the universe. Good. And I promise to keep us on time for ending early today, no matter what. Okay, who's next?